Okay, hello everyone. In this video, we are going to be talking of the different thermodynamic process. Okay, um, in our previous video, we looked at the first law of thermodynamics. Okay, now that first law of thermodynamics can be applied in different processes. So we have four thermodynamic processes here. We have isothermal process, which means constant temperature, isobaric, which is constant pressure, isochoric, constant volume, then adiabatic, constant heat. So we are going to be seeing each of them and know what the values of internal energy, heat, and work done are for each of these processes. Okay, here we see the isothermal condition. Now, in the isothermal condition, it means that the heat, the change in temperature is zero. Okay, that means temperature is constant. And if temperature is constant, delta U is zero. I said earlier in one of the videos, you can watch that where I explained the concept of thermodynamics. The internal energy depends on temperature. So when temperature does not change, the internal energy too does not change. So internal energy is zero. Okay, and so since our change in internal energy is equal to Q minus W, and the change in internal energy is zero, which is equal to Q minus W, we can simply say that Q is equal to W. So the heat is equal to work done. Okay, then secondly, the work done by a system is given by this formula: W equal to integral V1 V2 P dV, integral P dV with our boundaries B1 V2. Now, if the temperature is isothermal, then the whole of this formula is going to lead us to this, which is nRT ln V2 over V1, which you can write in different ways. You can also write it as nRT ln P1 over P2. So you can replace V1 over V2 with, V2 over V1 with P1 over P2. And that is because, according to Boyle's law, volume is inversely proportional to pressure. So V2 over V1 can be replaced with P1 over P2. Also, the nRT can also be replaced with P1 V1. So P1 V1 then ln P1 over P2. This is also very correct. And that is because, according to the ideal gas equation, nRT is equal to PV, or you say PV equal to nRT. Okay, so whichever way it comes, whichever quantity we are given, we can apply the formula correctly. Let's see just an example here. Here it says 2 moles of a monatomic gas at a temperature of 27 degrees Celsius expands isothermally. That's the key point here. From an initial volume of 10 meter cube to a new volume of 20 meter cube. What is the work done by the gas? Heat and change. Okay, we also asked to find the heat, sorry, that's a mistake, and change in internal energy of the gas. First off, I don't need to, it's an isothermal condition, so the change in internal energy is definitely equal to zero. That is standard. Then concerning the work, and we also know that the work done for an isothermal condition is nRT, then ln V2 over V1. I think this works here. Now, N, which is 2 moles, we are given 2 moles of gas, so 2. R here represents gas constant. Gas constant is 8.314. Okay, then multiplied by the temperature is 27 degrees Celsius. We convert that to Kelvin. That will give us 300 Kelvin. Okay, then we have ln V2 over V1. Our V2 is 20 and our V1 is 10. Okay, so that would give us okay, so you can do the calculation and send the answers on the comment section. Okay, so that is it for isothermal condition. Now that, okay, and one more thing, the heat there is definitely equal to the work done based on our definition. So heat equal to work done. Okay, So here we see another question. It says a balloon contains 5 mole of a diatomic gas. Its temperature is kept constant at 20 degrees Celsius, while the balloon contracts to 40% of its original volume. Okay, so that means that, okay, find the work done by the gas in expanding the balloon, the heat, and the change in internal energy. I've told you earlier, change in internal energy is equal to 0 because we are dealing with isothermal condition. We are told that the temperature is kept constant. Okay, but now to find the work done in this case, we can still use nRT ln V2 over V1. N is the number of moles, which is 5 moles based on the question 5. R is gas constant, which is 8.314. Okay, then multiplied by the temperature is 20 degrees Celsius. Converting to Kelvin will give us 293. Okay, then ln V2 over V1. Now the contraction is by 40%. Okay, and so we can say the contraction is, when you say it decreases by 40%, what does that mean? It means that V2 is equal to 40%. Are we going to say V1 minus 40% of V1, or 40 over 100 of V1? So that's what that means. It contrasts. Okay, it contrasts to 40%. Sorry, this is not correct. So since it contrasts to 40%, that means V2 is equal to 40% of V1. Okay, what mean? Well, that means, which is 0.4 V1. V1. So what that means is that V2 over V1 is 0.4. So I can come here and say then 0.4. So please, you can calculate that. Give me the answer in the comment section. Okay, so that leads us to the next concept. The next condition, the next process we'll look at here is isobaric condition. Now, in isobaric condition, remember I said earlier that the work done is integral of P dV, then we have V1, V2. If pressure is constant, I don't want to go through the processes on how that is gotten. But if pressure is constant and you know your integration, it means that your P, which is constant, then dV, integral of dV, will give us V and will lead us to V2 minus V1. So that means the work done in an isobaric condition is pressure times change in volume. And so since the internal energy is equal to heat minus work, we can simply say it is equal to heat minus P into V2 minus V1. Okay, which is exactly what we have here. Okay, so we see this question. It says a gas is compressed at a constant pressure of 50 Newton per meter square from a volume of 10 meter cube to a volume of 4 meter cube. And the energy of 10 joules then added to the gas by heating in its internal energy is, okay, first off we have, this is compression. I want to know this, want to let you know this. The work done that is done by the system can either be for compression. If it is compression, it means work is done on the system. If it is expansion, it means that work is done by the system. Okay, but a gas is compressed at a constant pressure of 50 newtons per meter. So my P is 50 newtons. Or let's start by stating the formula for work. The work is P into V2 minus V1. P is the constant pressure, which is 50. Then V2 minus V1 is 10 minus 4. Notice that all the units are in SI units, so make sure that your units are in SI units. Okay, so this will now be 50 multiplied by 6, and that will be 300. So the work done is 300 joules. Then we are asked to find the internal energy. So we say that, we can say here that internal energy is equal to Q minus W. Now the Q here is, we're given that energy of 10 joules is added to it by heating. So that means that is 100 joules. The minus W. W here is minus 300. Now you're going to wonder, why is it minus 300? I told you earlier something about compression, because it is being compressed. When the gas in a piston is compressed, it's not done by the internal, it's not done by internal, it's actually done externally. Because usually when you add heat to a system, there is meant to be an expansion. The piston is meant to increase. But compressing means that somebody is doing, or work is done on the system to compress the system. So that's why we have negative. And so 100 minus 30 will give us 400 joules. Okay. Now let's see another question here. It says 1 mole of an ideal gas initially kept in a cylinder at a pressure of 1 megapascal at a temperature of 27 degrees Celsius is made to expand until its volume is doubled. Okay. How much work is done if the expansion is adiabatic, isobaric, isothermal? Then the B part says identify the processes in which the change in internal energy is least and is maximum. Oh, this is beautiful. Okay, so first of all, in this video, we are not going to be looking at the adiabatic condition. I will be making a separate video for that. Okay, but if it is isobaric, the work done is equal to pressure times the change in volume. Okay, and we are not given any volume here. Okay, they said the volume expands, is doubled. So we can say that the pressure is 1 megapascal, which is 10 raised to power 6 Pascal, times the change in volume. We are not given the volume, but we can find the volume knowing that PV is equal to nRT. So that means V now will be nRT divided by P. Okay, the number of moles is 1. The gas constant is 8.314. The temperature is 300 Kelvin. That's because 27 degrees Celsius. And divided by the constant pressure is 1 megapascal. That's 10 raised to power 6. Okay, this gives us 2.5 times 10 to the power minus 4. Okay, 10 to the power negative 4. Okay, so that is our volume, and that volume there is V1, but we are told that it is made to expand. So made to expand by twice its volume. So that means V1 is equal to 2.5, sorry, times 10 to the power minus 4. That means V2 is going to be 5 times 10 to the power minus 4. That's double of that. Okay, so let me rub this off quickly. So what that simply means is that my work in the isobaric condition, W is equal to, the pressure is 10 raised to the power 6 into 5 times 10 to the power minus 4 minus 2.5 times 10 raised to the power minus 4. Okay, that's going to give us 10 raised to the power 6 times, this would give us 2.5. 5 minus 2.5, 2.5 times 10 to the power minus 4. And that will give us 2500 joules. Okay, that is beautiful enough. 2500 joules. That is the work done. And since the condition is isobaric, we need to find the heat. Let's leave that for now. Okay, so then the work done in isothermal condition, we can say W equal to nRT ln V2 over V1. N is 1, R is 8.314, T is 300. But now ln V2 over V1, V2 over V1, they say V2 is twice that of V1, so this should be ln 2. So we can use our calculator to get that. And that will give us 1728.8. Okay, so this video we may not be able to answer the B part of the question, which is the internal energy in each cases. That is because we did not cover the scope here. Okay, so I'll be posting more videos. Thank you.